Okay, heptadecane can be extracted from crude oil or cactus plants. Write an equation for the complete combustion of C17H36. I have a nifty trick how to do equations like this. It's in the SL video. Yeah, if you want to see it, SL video. Otherwise, this is the answer. C17H36 plus 26O2 forms 17 CO2 plus 18 H2O. There we go. Yeah. The trick basically involves using these numbers to determine the coefficients for these different reactants. Yeah, just for the sake of time, just refer to the other video, SL video, if you want to know how to do this quickly. Okay, and enthalpy of combustion is minus 11,350. Maximum energy produced when that much is combusted. So remember, this combustion is kilojoules per mole, but we don't necessarily have 1 mole in 2 grams. So we have to calculate how many moles we do actually have. So it's C17H36. So we do 2 grams, which is our mass, over the molar mass of whatever this is. So it's going to be 17 times 12.01 plus 1.01 times 36. Okay, that gives us 2 over 40.53, blah, blah, blah. So that gives us 0.008315 moles, right? So that's our number of moles, and we know that this is the energy, the enthalpy, if we had 1 mole. So essentially we're just multiplying this 11,350 by our moles, 0.0083 blah blah blah, gives us 94.4 kilojoules. Okay, determine the maximum temperature change when 500 cm cubed of water is heated by a 2 gram sample of C17H36. Okay, so we have our energy here, 94.4. That is going to be 94,400 kilojoules. 94,400 kilojoules. That's an energy now, remember, because this was enthalpy because it was per mole, but this is our energy now because it's that. So we're using Q equals MC. I'm just going to rearrange that. Equals our mass of, so 500 cm cube of water. Well, we'll assume it's 500 grams. So 500 grams is our mass of water times C, which is 4.18. And then our delta T is our X. So yeah, we rearrange and we get a delta T of 45.2 Kelvin. Outline 2 assumptions that were made in the calculations. An easy assumption is that we assume that 500 cm cubed of water is 500 grams of water. So that essentially is the assumption that the density of the water is 1 gram per cm cubed. What else can we assume? Well, we're also assuming that no heat is lost to surroundings. What else can we say? Well, you can also assume the water doesn't evaporate during the reaction. You also have to assume that the reaction continues until completion, meaning that it is a complete combustion reaction. We're also assuming that all the heat's transferred to the water. There's not other heat transfers occurring, which also applies to this one. We also assume that the water is pure. There's no impurities there. Explain why biofuels contribute less to climate change than fossil fuels. This is just to be the nature of how biofuels are made. Remember, they're made from plants which undergo photosynthesis, right? So the plants undergo photosynthesis, which uses up CO2. CO2, then releases it later. So net effect is low, right? When you have a fossil fuel, right, we're taking something that wasn't in the atmosphere before, and we're essentially releasing it to the atmosphere, right? It was stored in the ground, and we're releasing it to the atmosphere. When we have fossil fuels, it's going to be something that took up carbon from the atmosphere. Now we're re-releasing it, so it's net, pretty much net neutral. Okay, heptadecane can be broken down into smaller molecules. Consider the reaction. This determine the sign and enthalpy change of the reaction using section 12 of the data booklet. Section 12 is the bond enthalpy section. Again, I don't have the data booklet with me right now. It just disappeared from my iPad, like my menu. I don't know where it went. Essentially, bond enthalpy. Again, I did this question in the standard level paper, so if you want to see it again, I did it there. But basically, you're just looking at how this one is essentially quite similar. We're just losing 4 carbons and it's forming this C2H4. So we have to think about the bonds that we're losing here, right? So we're losing 4 carbons or so, where essentially where the bond's broken is going to involve 4 times 346, which is the C single bond C, right? So C single bond C, we're losing 4 of those. So that's our bonds broken, equals BB. And then our bonds formed, well, we know that we have this C double bond C, right? So it's forming 2 times C double bond C, which is 2 times 614, equals bonds formed, right? And if you're wondering about anything else, remember the rest of the bonds already existed in the original molecule, so we don't need to account for that. We're just talking about the new bonds broken, new bonds formed and the old bonds broken. We know that 4 carbon-carbon single bonds were broken, and we know that the only new bonds here is this C double bond C. There's 2 of them, remember, because there's a 2 here. That's why there's 2. But yeah, okay. And from that, we just do reactants minus products, and then yeah, we'll get a value of 156 kilojoules. Determine the enthalpy change of reaction. Use the data provided in section 13 of the data booklet. So this is just formation values. We know that it's products minus reactants, okay, and we know that this one is 393.9, this one's 311.5, and then we're just missing this C2H4, which we'll get from section 13 of the data booklet. So if you check that section, you should get this formula. So delta H equals 2 minus 1311.5 plus 2. Remember, we have this 2 here, so 2 times 52, which is our formation for the C2H4, and then that minus 393.9. And that, oh, sorry, there's a minus on MS here, minus 393.9, and that gives us a value of 186.4. Okay. Comment on the difference between the 2 values calculated. So in DI. So in DI, we have a 156, and this one we have 186. So they're quite close, but they're different. Why are they different? Well, DI was calculated using bond energy values. II was by using formation. So which is more accurate? Well, we know that DII is more accurate. Why? Because bond enthalpy, bond energy, averaged over similar compounds, right? So you have a couple similar compounds, right? They average the bond enthalpies, and then that's how we're getting this C single bond C. That's how we're getting the value for the single bond, and then C single bond H. They're just averaged over the similar compounds. So it's relatively specific, but if you take it against something like a formation is specific to that exact compound, right? And bonds behave differently when they're in different compounds. So this is kind of a general classification, and this is the very specific one. So enthalpy of formation is always going to be more accurate than the bond energies. Okay. Predict the sign of the enthalpy change of the reaction, giving a reason. So yeah, so we have 3 moles of gas here, 1 mole of gas in the reactants, so it's going to be a positive due to increase in number of gaseous moles or moles of gas. Discuss with reference to DII and DIV how temperature affects the spontaneity of the reaction. Okay. So with reference to DII and IV, II proves that it's going to be a endothermic reaction. It has a positive delta delta H IV shows that it's going to be a positive entropy change, right? So it's positive, right? And we have delta H minus T delta S equals delta G. Delta H is positive and T delta S is positive. What does that mean? That means that at the higher, if we have a higher temperature, right? So this is positive, this is positive, right? So it might, let's just substitute 2 and actually, I don't even need to substitute. You can kind of tell, right? So if we have a positive number here, subtracted from this, which will stay negative, right? Because this is minus T delta S. It'll still be negative because delta S is positive, right? And our T is going to be positive. So it's going to be delta H minus something, right? If we had a negative delta S, then this would become a plus, and then it would become confusing. But no, it's also, this one is positive. So that means that if we have a higher temperature, right? That means that our delta S is going to be higher. Our T delta S is going to be higher. That means this is going to be subtracted from delta H by a greater magnitude, and that means that our delta G will be lower, more spontaneous. So what does that mean? That means that, so let's identify first. Our delta H is greater than 0 and delta S greater than 0. Okay? So, and we know the reaction is spontaneous if delta G is less than 0, right? We have this equation here. So this means that at a higher temp, the reaction will be more spontaneous because it'll be more negative in terms of the delta G. That's how we get it. Okay, ethene can be converted to ethanol in one reaction. State the equation for this reaction. Okay, it's a pretty standard equation. C2H4 plus H2O from C2H5OH. Throw in the state symbols at your own discretion. Okay, ethanol reacts with oleic acid to produce ethyl olate. I literally pronounced it wrong in the SL video as well. So that's quite impressive for me. But yeah, okay. Identify the reaction in the side product X. So we can see that it's a carboxylic acid and an alcohol. This is an esterification reaction, and that our product is going to be water. Okay, atom economy. So for the atom economy, we're basically looking at the desired product and desired reactant, how much we have of each. Essentially, we're gonna just calculate the amount of desired product and the amount of that's just a formula. It's in the data booklet. Okay, basically we get to calculate the total mass of desired product. It is, so this is 17, so there's 20 carbons, okay, 20 carbons, 38 hydrogens, and 2 oxygens, okay? So that's the total atoms we have in the products. So now we just get the mass of that, so 20 times 12.01, 38 times 1.01, and 16 times 2 for the oxygen, and that gives us 310.58. Okay, so then we do 310.58 over 310.58, so which is this, so that's this, right? But we're gonna do, so it's basically the desired product is 310.58 plus the total product also includes the water. So the water is kind of the extra thing that we have here. We don't really need it. We're looking for this desired product. So the reaction is just a simple like percentage desired over total. So the side product is just water. So we add the 18.02, right, for water, H2O, and then we'll times this by 100, and we'll get 94.5%. Discuss why the atom economy of a reaction is an important consideration when evaluating the impact of a reaction in an industrial process. Strange question again for chemistry. I mean, you always see these questions every year. I just find it strange. But yeah, so many things you can say. You can talk about sustainability. Sustainability. Talk about sustainable development. You can talk about reduction of waste. you can talk about efficiency, right? It's more economically efficient. We're using our resources better. We can talk about like it being a better use of our natural resources. So many things. Just say something that makes sense. They'll give you the mark. Okay, deduce the equilibrium constant Kc of the reaction, or the expression of the reaction. Assume the reaction is homogeneous. Okay, so we have our K, and then we just putting the products on the top, so it's this long thing, C17, blah, blah, blah. I'm not going to write it out because I'm lazy, but so that product, and we have water, and then that's all over our reactants. Oh, wow. Yeah, that's an interesting fraction there, which is our C17 and our CH3, yeah. So it's the other C17, blah, blah, blah thing, and then the CH3 thing. There we go. You guys know how to do an equilibrium constant expression. I shouldn't have to explain it. And remember that there's no coefficients here, so there's no exponents in our expression. Okay, the equilibrium constant Kc is 9.3 times 10 to the minus 5 at 75 degrees C. Determine the amount of ethyl alloy, amount of ester present in the reaction mixture at equilibrium when 0.1 mole dm cubed of oleic acid reacts with 0.1 mole dm cubed of ethanol at 75 degrees C, and state any assumptions you have made in your calculation. Oh, it's almost wrapping there. But yeah, just a long question, but it's very simple. It just seems intimidating because of the way they phrase it. I thought they would give you more than 2 marks for this, to be honest, but you know, you get what you get. So how do you solve this? So we first have to look at our Kc. You can see that it's very small. It has a times 10 to the minus 5. It's very small. That indicates that the reaction strongly favors the reactants. Essentially, it means it's not going to progress very far in the forwards direction. So this means that there'll be a very negligible change in the concentration of reactants. So this tells us we basically already know our equilibrium concentration for reactants. So we know the initial here, 0.1 mole dm cubed, 0.1 mole dm cubed. What this small Kc is telling us is that 0.1 mole dm cubed, right? That minus x, right, is going to be our equilibrium concentration. But this small Kc is telling us that this x is so small, so tiny, its magnitude, that we can basically just assume that this 0.1 is the same. It's the same. It's like it's still 0.1. So that is mighty helpful for us because it means that we can skip a lot of the difficult parts and we can just go straight to the fact that we know that the Kc equals, we know that on the top we have these two are ester and our water, and they're in 1-to-1 ratio, so that's our x squared over 0.1 times 0.1. That skipped us a lot of hassle, a lot easier now. So what do we do now? We know the Kc already. 9.3 times 10 to the minus 5, 9.3 times 10 to the minus 5. We can move this 0.1 times 0.1. That gives us 0.01. And then we have this squared, right? So we can just square root all of this, okay? And that gives us a value of square root of 9.3 times 10 to the minus 7, and that gives us our final answer of 9.6 times 10 to the minus 4 mole. Mole dm minus 3. Yeah, nice. State one method of increasing the yield. There's so many ways you can think about this. I was just trying to think in my head what I would say. Yeah, it's quite a general question. I would probably just think the easiest one is just to remove the water. Remove water, because water's our undesired product, right? We remove the water, we're going to increase the yield. We'll clear that part up. How else? Well, we have our two reactants here. Just add more of them. So increase the amount of oleic acid, acid plus easy way. Okay. Halogens are important reactants in the laboratory and the environment. Write an equation. Homolytic fission. This was again in the SL paper, but I'll do it because it's quick. Homolytic fission looks like this. Equal transfer, but remember, we're doing the fishhook arrows because it's equal, so we're taking one each. We're not taking a pair. We're doing an equal distribution, and that gives us these two radicals. My drawing isn't the best, as you can tell, but just do it better than me. Okay, this one is heterolytic fission. Oh my gosh, I'm losing my mind today. Did I do Cl here? Yeah, I did Cl. Cl, much easier. You can do the double barb here, and yeah, and that gives us one Cl plus and one Cl minus. Yay. Identify giving a reason which one of these three species produces an AI and a double I is an electrophile. Well, we know an electrophile is going to be Cl plus. Why? Because it can accept a pair of electrons to form a new bond, right? So it can accept a pair. We know electrophiles generally, they do accept pairs of electrons. Draw the full structural formula of the most stable carbocation formed in the reaction between hydrogen chloride and propene. Oh, wow. Yeah, so we know that the carbocation formed, carbocation is going to have this positive charge in one of the carbons. The most stable one. Remember, this stability is due to positive inductive effects, right? So we're essentially just trying to maximize positive inductive effects. So we want the charge on the carbocation, we want it on the central atom, so we have the opposing methyl groups, right? We want these two methyl groups on the side. We want them to be able to give us these positive inductive effects. So how do we draw it? Well, we should have this central one be our carbocation, so let's just mark it immediately, and the rest we just fill out with H's. That gives us this carbocation, which is the correct answer. Okay, outline why this intermediate was... Oh, that's literally what I... Yeah, so I basically said this answer already. Positive inductive effects. And this is from these two side methyl groups. This is what provides us this inductive effect. This graph shows the boiling points of the first 5 straight chain primary alcohols and fluoroalkanes. Outline why alcohols have a higher boiling point than fluoroalkanes of similar relative formula mass. Why? Because H bonding. Okay, hydrogen bonding is stronger than DP forces. Okay, and alcohols have hydrogen bonding. Fluoroalkanes have dipole forces only. Hence why they have higher boiling points. Explain the general trend in boiling points shown for the alcohols. So you can see that the alcohols, they're increasing in boiling point as per increasing the formula mass. So why does this happen? Well, it's because our LDF is higher. Our London dispersion forces, they're increasing. But why are they increasing? Well, we're having increased electrons, right? Increased electrons increases our London dispersion forces, and our electrons correspond with our relative formula mass. So we're increasing this, we're increasing our electrons. So higher electrons means, bigger LDF. Predict giving a reason how the boiling points of branched fluoroalkanes compare to their straight chain isomers, okay? So how would branched straight chain? This is pretty easy. We know that branched will have a lower boiling point. Why? The compact shape, right? Because straight chain maximizes this shape, right? The size, right? When we have branches, we're compacting the shape. So the compact shape will essentially reduce the contact area, right? And this is what also reduces our London dispersion forces. Reduces the contact area, and that's going to reduce the London dispersion forces. So we want the maximal area, right? Just always remember the branch is always going to be a lower boiling point than the straight chain isomers. Explain why primary bromoalkanes have higher boiling points compared to the corresponding fluoroalkanes. Why? Primary bromoalkanes. Oh, this is quite easy. So this is just simply because it has more electrons. So more electrons have higher LDF. I assume that's what it wants us to refer to. Primary bromoalkanes have higher. Yeah, I'm pretty sure it's just, higher. More electrons is higher LDF, and more electrons, you find that out by just looking at the formula mass. Pretty simple question, honestly. We'll draw the structures of 2-bromobutane and its tertiary isomer. Okay, 2-bromobutane, interesting. So we should have, it'll be a CH. So this is the 2, and then we have our butane, so it's, this will be a CH3. I won't draw the hydrogens just for the sake of simplicity. Br, so that's our 2-bromo, and then butane, so this will be a CH2, this will be a CH3. So that's our 2-bromobutane, and then tertiary isomer. So tertiary isomer, it'll have this central carbon. So it's tertiary, it means that it'll have a carbon on every side. So it'll have a CH3, 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 okay? And then this will be a bromine. And this is also a term 2-bromobutane because of the fact that we just think the longest chain is always going to be 2, and it's always going to be connected to this carbon that's connected to bromine. So yeah, this is a tertiary 2-bromobutane. One of the isomers in CI exists as enantiomers. Draw their stereochemical formulas. So you should be able to identify that the one that has exists in enantiomers is this one, because that we have this distinct groups. We have a H group, which is unique, Br group unique, CH3 unique, C2H5 unique, right? So we have 4 unique groups, which means that it will have enantiomers, right? So we need to draw their stereochemical formulas. I assume they want us to draw it with our dashed and wedge notation, so I'll draw our mirror here, okay? So we'll draw our wedge coming out. We'll draw our dashed line. We'll draw our straight line. We'll draw just a regular line. And so we can have our bromine here. Then that means we'll have our CH3 here. And that means that we'll have our H here and our C2H5 here, okay? Or our CH3, CH2. And then the enantiomer will just be this. So our Br is still here. Our CH3 is here, not here. Our H is not here. And our C2H5 is not here. There we go. Iron HR spectra, circle the regions which indicate the presence of bromine atoms. Use section 20 and 21. Okay. This is an issue because I don't have the data booklet up. But this is just, essentially, you'll just look at section 20 and 21. You'll find the wave number that corresponds to bromine. It'll be here. Okay? Just double check, do it yourself, and check it. Okay. As for this one, you're checking the ppm, presence of bromine atoms. So again, you're checking the presence of bromine atoms. You should be able to find it here. Yeah. Explain whether the IR and HNMR spectra can be used to distinguish the tertiary isomer from 2-bromo-butane. You don't need the data booklet for this, so I'll explain it. Okay. So the IR, if you think about it, it won't be able to distinguish it. Why? The IR is giving you bonds, right? So if you think about the bonds that we have in the 2, I just realized we drew them already. So you think about the bonds we have in the 2. Do we see any distinct bonds here that we wouldn't find in the primary, that we wouldn't find in the tertiary? I don't see any. Yeah. Sorry, I didn't mean to say primary, but yeah, I meant this one versus this one. So 2-bromobutane, right? It doesn't have any bonds that the tertiary version doesn't it doesn't have any bonds that the tertiary one doesn't have either, so they have the same bonds. This means that we can't use the IR due to same bond. Okay, HNMR. Explain whether IR and HNMR spectra can be used. Okay, so the HNMR, right? We can do it. Why? Yes, because unlike our 2-bromobutane, because of the way it's structured, this one will literally just be one signal, right? We would see one signal, right? Because this one's all these different groups. This one only has, just look at it. It has the CH3, 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 and then one Br here. So it will literally only see one signal, one peak, and that's what's going to differentiate the two of them. So yeah, I think that's it. Yeah, lovely. I kind of sped through at the end. Forgive me for that. I have to go somewhere soon, so I just kind of went extra fast. But if you don't understand anything, just please ask me in the comments. I'll go through it. And one thing as well, for this, I was thinking about it for this equilibrium question back here. There are equilibrium questions where you can use a technique known as ICE. It stands for initial change and equilibrium concentrations. We don't have to use it here, but you can use it for different questions. And I was thinking, some of you might not know that technique. So if you would like to see a video on ICE, please let me know, and I will make it. That might be a good one. But other than that, pretty simple paper, not too different from the SL actually. And the differences were pretty simple, pretty easy. So yeah, I hope you enjoyed this video. I'll make a new one soon, and hope you enjoyed. Good luck with your exam, everybody. See you.